Welcome to This Explainer. Today, we're diving straight into the fundamental mystery of matter and how one scientist's totally radical idea literally saved the universe from classical collapse. Think about the chair you're sitting in right now, or the screen you're looking at. For centuries, we've just taken the absolute stability of these everyday objects for granted. But, as we'll uncover today, peeling back the layers of the invisible world revealed a terrifying paradox.
I mean, why doesn't the universe just collapse? It sounds like some kind of philosophical riddle, right? But back in the early 20th century, this was a massive, genuine scientific crisis. The established laws of physics practically guaranteed that the very atoms making up our bodies, our world, and our stars should just self-destruct in a fraction of a second. So how on earth are we still here?
Let's get right into Section 1, the crisis of the atom.
To really grasp this crisis, we've got to track how humanity's understanding of the invisible world accelerated. For millennia, the atom was just this theoretical concept. It all started way back around 400 BC, when the Greek philosopher Democritus proposed atomos, literally uncuttable particles. But things rapidly sped up in the 19th and 20th centuries, as science proved that atoms were not only very real, but actually had incredibly complex internal structures.
It's kind of wild to think about how simple it all started out. John Dalton provided the first modern scientific framework back in 1803. He basically imagined atoms as solid, indivisible billiard balls that dictated chemical reactions. It was elegant, you know? It made total sense of how elements combined. But it assumed the atom was the absolute end of the line, that there was absolutely nothing smaller.
But then, of course, we found something smaller. When J.J. Thomson discovered the tiny negatively charged electron in 1897, he totally shattered the idea of indivisibility. So in his 1904 plum pudding model, he proposed a structure where these negative electrons just sat in a diffused positively charged sphere, basically just to maintain overall electrical neutrality.
It was almost as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. That famous remark from Ernest Rutherford perfectly captures his sheer disbelief at the results of his 1911 gold foil experiment. He fired positively charged alpha particles at a super thin sheet of gold, fully expecting them to pass right through Thomson's soft plum pudding. Instead, some violently bounced back. Rutherford realized the atom's positive charge and mass had to be concentrated in a tiny, incredibly dense center. He had found the atomic nucleus. So Rutherford essentially likened the atom to a miniature solar system. But there was a fatal flaw here. Classical electromagnetism strictly dictated that accelerating charged particles, like these orbiting electrons, should continuously radiate energy. And as they lose that energy, they should instantly spiral right into the nucleus. Boom! Atom collapses, matter shouldn't exist. This was the ultimate crisis of the atom.
Which brings us to Section 2. Bohr enters the fray. Solving this massive paradox required a completely new way of thinking. Enter Niels Bohr. He was raised in an intellectually vibrant household in Copenhagen. His father, Christian Bohr, was a celebrated professor who constantly hosted leading scholars. So young Niels grew up surrounded by intense scientific and philosophical debates. This really nurtured a highly collaborative and rigorous approach to problem solving. He was a rising star, even winning a university gold medal for his early research.
After earning his PhD, Bohr actually traveled to England. In 1912, he joined Ernest Rutherford's dynamic laboratory in Manchester. And it was here, surrounded by the top minds of the day, that the glaring instability of Rutherford's atomic model completely captured Bohr's focus.
Moving on to Section 3, the quantum leap. Confronted with an atom that by all known laws shouldn't exist, Bohr realized the solution was practically unthinkable. He had to abandon the absolute certainties of classical physics. While Rutherford's classical planetary model allowed for continuous orbits that would inevitably decay and collapse, Bohr looked to the emerging radical quantum theory from Max Planck and Albert Einstein. He proposed something entirely different from the macroscopic world we see around us every day.
In 1913, Bohr essentially hacked physics by publishing these 4 revolutionary postulates. First, electrons can only orbit in specific, allowed paths called stationary states. Second, and this is absolutely crucial, while in these allowed orbits, they simply do not radiate energy. He literally just rewrote the rules to prevent the collapse. Third, electrons jump between these orbits by absorbing or emitting precise, exact quanta of energy.
And fourth, their angular momentum is quantized, meaning their rotation is locked into strict mathematical steps. It was a bold move and a massive triumph. It perfectly explained atomic stability and exactly matched the specific wavelengths of light emitted by hydrogen.
1922. For this monumental breakthrough, successfully bridging the classical deterministic world and the completely weird probabilistic quantum world, Niels Bohr was awarded the Nobel Prize in Physics.
That leads us right into Section 4, the Copenhagen Spirit.
You see, Bohr's genius wasn't just in his solitary calculations. He was an absolute master at conducting a global orchestra of theoretical physics. In 1920, he founded the Institute for Theoretical Physics at the University of Copenhagen. This place quickly became the premier hub for quantum research in the entire world. And Bohr's leadership style, it was deeply unique. He created an environment that actively invited brilliant young minds to openly challenge established ideas, even his own.
And well, challenge him they did. The science evolved rapidly. The original Bohr model actually struggled with complex multi-electron atoms. Soon, Werner Heisenberg, who was one of Bohr's mentees, introduced the uncertainty principle. Erwin Schrödinger proposed treating electrons as waves. Ultimately, Bohr's rigid orbits were replaced by the modern probability electron clouds. Yet through all these profound debates, including some legendary clashes with Albert Einstein, Bohr's foundational concept of quantized energy remained the absolute cornerstone of it all.
Out of these intense debates, Bohr developed a profound philosophical insight: complementarity. He argued that the universe is inherently paradoxical. For example, light can act as both a wave and a particle. You can't observe both properties simultaneously, but you need both perspectives to fully understand reality. It was a beautiful framework for accepting the contradictions of the quantum world. And honestly, it's a pretty good philosophy for life too.
And finally, Section 5, Legacy in the Atomic Age.
As the 1930s dawned, Bohr shifted his gaze to the dense atomic nucleus, entering a period that would violently alter global history. In 1936, he proposed treating the atomic nucleus like an incompressible drop of fluid. The liquid drop model was a massive breakthrough. It directly enabled scientists to visualize and understand nuclear fission, how atoms could be split apart to release earth-shattering amounts of energy.
But, as we know, this theoretical physics soon became a terrifying reality. During World War II, following the Nazi occupation of Denmark, Bohr made a dramatic escape to Sweden and eventually over to the United States. Operating under the pseudonym Nicholas Baker, he consulted on the Allied atomic bomb effort at Los Alamos. However, unlike many others at the time, his primary concern was already focused on the terrifying, long-term implications of this world-ending technology.
Following the war, Bohr didn't just retreat to his chalkboard. He became a passionate, leading voice for global scientific openness. In 1950, he addressed his famous open letter to the United Nations, pleading for international transparency to prevent a catastrophic nuclear arms race. He firmly believed that only an open world could handle the awesome power of the atom.
His final years perfectly captured his dual legacy. He actively shaped peaceful research institutions, playing an instrumental role in the creation of CERN, for example. He worked tirelessly to ensure that his legacy was one of profound scientific truth, but one firmly guided by deep humanitarian responsibility.
Niels Bohr showed us that truly understanding the universe requires the courage to let go of what we think we know. He abandoned classical certainty for quantum probability, and in doing so, he changed our world forever. So I'll leave you with this. As we continue to probe the deepest layers of the microcosm, what long-held certainties will we need to leave behind next?